Hi, everyone. I'm Rob Rader, Director of Engagement and Membership here at AGU. Thank you so much for joining this Atmospheric Sciences webinar series. This is part 7 in the From the Past into the Future talk that was given at the 2019 AGU Fall Meeting. Today, we have with us a couple of speakers for you. So that will be, first speaking will be Jim Kossin to talk to you about detecting trends in tropical cyclones. And then our second speaker on today's webinar will be Duane Waliser, systems perspective on the environmental prediction enterprise. So we'll get started in a moment, but just to let you know, we do record these webinars. There are 8 webinars in this series. Will be recorded and archived on the AGU channel on YouTube. So feel free to check that out. You can also go to the Atmospheric Sciences website. Their webinars page will have all the links to these webinars and links to the abstracts from the talks as well. You will have opportunity to ask questions after each speaker for about 5 minutes. There's a couple different ways to do that using the question functionality or the hand raise functionality. So we can actually unmute you and you can ask your question on your mic. So with that, I am going to go ahead and give Jim control to present his slides. So Jim, whenever you're ready, thanks for joining us today. Really appreciate it.
Oops. There we go. Thanks very much, Rob. I'm going to back this up. Sorry about that. You
Good to
can
go.
see my screen okay? Yeah, every time I click to click anything, I switch out of presentation mode. So let's see. Okay, how we doing now?
Looks good to me.
All right, great. Thank you, Rob.
Sure.
Yes, hello everybody. I hope you're all staying healthy in body and in mind. The latter of the two is probably a challenge for a lot of us at this point. Thanks for attending. So this is a talk that's kind of a general overview on some of the progress that we've been making towards detection, particularly past trends in tropical cyclone behavior in general. So I'm with the NOAA NCEI, which is has multiple sites. My duty station is at the Cooperative Institute at the University of Wisconsin here. So just in general, and I think I'm probably preaching to the converted here, but in terms of what detection and attribution, what we would like to have for this with detecting and attributing changes in tropical cyclones is we'd like to have good physical process understanding. And we do actually. We have a pretty good idea of how tropical cyclones respond to their environments. And so as the environments change, whether through natural variability or anthropogenic forcing, we do expect the tropical cyclones to change their behavior as well. We rely on numerical simulations, past and projected. And then we would like to have observed changes that we can demonstrate are not readily explained by natural variability. So the trifecta would be that if we have consistency and agreement among these, then we start to get pretty high confidence that there are detectable changes that we could attribute to human causes. So of course, the better confidence why we want it is ultimately we would like to have confidence to galvanize adaptation measures and things like that, building resilience. So what are some of the physical processes that we have pretty good understanding of, which gives us sort of an a priori expectation of what might happen under warming conditions? Certainly warming sea surface temperatures we know has, especially it's a strong effect on how strong a tropical cyclone can become. So it plays a key role in setting the sort of the thermodynamic speed limit of how fast the winds can blow in a tropical cyclone. We know that if we increase potential intensity, then you tend to get a shift of the TC intensity distribution. And in particular, the stronger TCs tend to get stronger, and the proportion of major TCs tends to increase. Like most things where you're shifting a distribution, there may be a relatively small change in the mean. So in terms of the average wind intensity, and when I say intensity, generally I'm talking about surface wind speed is generally what we measure. So the surface wind speed on average may not change much, but you can of course get pretty big changes in the tails of the distribution. The other thing that we have a good understanding of is that as we warm the atmosphere, we increase the amount of water vapor that it can hold, and that will relate to increased tropical cyclone rain rates. Tropical cyclones are very good at converging low-level moisture into one spot, namely the eye wall of a hurricane. So you increase water vapor, you increase rain rates. We also have a pretty good idea that the tropics are expanding, and since the tropical cyclones are creatures of the tropics, we would expect also there could be some polar migration of tropical cyclone tracks that go along with that. There's perhaps a general a priori expectation for slowing general circulation in its most base state. We might say Arctic amplification decreases the temperature gradient, which ultimately decreases the speed of the general circulation patterns. And if that's true, since tropical cyclones are pretty passive and are carried along for the most part in the background circulation, if you slow the general circulation, you would expect that you would slow down the tropical cyclones and how fast they move from one point to another. So that's what we have pretty good process understanding for. We don't have very good understanding for TC genesis. We're still kind of working on that. So that's an area of active research, of course, but that one we have less understanding of than some of these others. And there's other metrics that matter, but we don't really necessarily have a strong theoretical background for expecting size or related storm surges to change, although we can certainly still measure those things. Okay, just kind of a cartoony thing here. In a broad sense, you can kind of separate the historical record of tropical cyclones as far as, all the past research that we have literature in. If you go back about 1,000 years before present, then, you're into the realm of what's called paleotempestology, where you can use methods such as measuring overwash sediments to get an idea of how many hurricanes have impacted a particular region where you're taking these sediment cores and setting them. Oxygen isotope ratios in stalagmites and caves. The rainfall that comes out of tropical cyclones have a fairly unique isotope ratio because of the way things are depleted in them. So you can actually find tropical cyclone passages by studying these stalagmite, very much like tree rings. And tree rings is also a way that we can study these. If we want to go back, say, 100 years, on the order of 100 or hundreds of years, then we have things like personal journals. Jesuits in particular were going to all of these various islands in the tropics that are impacted by tropical cyclones, and they were very good at keeping personal journals, ships logs, newspapers, things like that. So you can sort of cull information and get an idea of what sort of tropical cyclone activity you might have had in the past. But then ultimately we come to the instrumental records, which started about 1850 and are continuing to present. And what this is what most of the work is done with. This is a what's called the best track instrumental record. And what it does is it gives us the position of the storm center and the intensity, again, that surface wind speed every 6 hours. And this is global, but the problem is that it's highly heterogeneous in time, and it's also heterogeneous by region. So it's a very difficult data set to work with when you're trying to detect trends, because you never know how much of it is technology based and how much of it is physical. Now, the best track data that are generally considered reliable, or at least more reliable, are global tropical cyclone counts since the advent of geostationary satellites. We don't miss them so much once those satellites are down there looking at the tropics all the time. So that's generally considered reliable. North Atlantic tropical cyclone counts over the United States since about 1900 is considered a subset of reliable data. And North Atlantic tropical cyclone intensity since the late 70s is considered to be fairly homogeneous as well. The global intensity estimates are very problematic, and they continue to be. Every year, there could be new instruments that are being used to measure this, and there isn't really any careful calibration being done to create a climate data record. And so it's kind of the Wild West out there. The measurements are being taken, but every year they could have new technological advances in them. So this is problematic for global intensity measurements. Okay, so in terms of what we do have some confidence in, you can see here on the top panel on the left is the global number of these best track estimates. And there's a very, very clear trend up to around the advent of the geostationary satellites, and then it gets pretty flat. And so we can be pretty confident that that trend is not physical, that it's based on technological advances and our ability to measure these tropical cyclones with increasing completeness. So not much of a trend there in frequency. And in fact, that corresponds to what we know in terms of what the numerical models suggest. The numerical models will, many of them will actually predict no change in global tropical cyclone frequency, or even a small decrease. There are some models that will project an increase, so the jury is still out on that. But at this point, we don't have an a priori expectation for an increase in frequency, and that's an important thing to remember. If we look at the continental U.S. landfalling hurricanes, as I mentioned, the data are considered reliable back to about 1900, and there isn't any really clear trend going on there. But again, we're not sure that we should expect one, right? We don't really expect a change in the frequency of these storms. We do expect a change in the intensity, but not necessarily the frequency. There's also track shifts that can affect what we're seeing there on the right. And so it's kind of difficult to interpret what that means. But we certainly, from the point of view of how much exposure the U.S. has had to landfall and hurricanes and major hurricanes, there isn't a clear trend there. And then finally, the North Atlantic intensity measurements since the late 70s are considered fairly reliable. And this shows how they have changed between the first earlier periods and the later periods in the North Atlantic. And what this is showing is basically a cumulative probability distribution or exceedance probability. And you can see that in the later half of the period that we're looking at, there's a clear change in the probabilities of finding these high wind speeds. And so again, this is it's important to note that the mean intensity in the North Atlantic only increases by about 3 knots. So if that's the only metric you're looking at, then you might say, well, there's not really much of a change going on there. But if you look at the way the distribution changes, there's a huge difference, huge increase in the probability of exceeding 100 knots. And 100 knots is the cutoff for major hurricanes. And those are the ones that do the most damage. Those are the ones that have the high mortality rates. Those are the ones that really matter. And so this is clearly a very strong signal and a very deleterious one as well. Okay, so it's unequivocal that we have these increases in tropical cyclone activity, these increases in tropical cyclone intensity in the North Atlantic since the late 70s. But what's not so clear to us is how to attribute those changes. And we face the issue, particularly in the Atlantic, of a very pronounced multi-decadal signal. And there's a very active debate going on right now about what is driving that. what we're looking at there is the MDR is the hurricane main development region in the North Atlantic. And you can see that we've gone through a warm period, a cool period, and a warm period. And I think most people in this audience are probably aware of this, this decadal variability. How it affects hurricanes and major hurricanes, you can see on the right there very, very dramatically. You get an active period of major hurricanes, a quiet period, and then another active period, which is the contemporaneous period that we're in now. So we clearly have a strong signal, and we clearly have a strong reaction of tropical cyclones, but what we don't have as clearly is exactly why we have this variability. And this is one of those things where a lot of literature is coming out on it almost every day, it seems like. And instead of the literature driving us towards a consensus, it seems to be somewhat binary. And for every paper that says it's almost entirely externally forced, there's another paper that says most of it is internal variability. So it's kind of uncertain right now exactly what is going on there, and there's really good arguments for both. But for now, it's a very active area of research. Okay, so I had mentioned that global intensity is the instrumental best track record is not very helpful for that, because the technological advances have been ongoing and without any real recalibration or reanalysis at the end of the year or anything like that. So it's very, very heterogeneous. And so any trends that we measure in the best track data are highly suspect. So what we could do is since the excuse me, the advent of geostationary satellites, again in the late 70s, we can create a homogenized a data record globally of tropical cyclone intensity by homogenizing the global satellite data. Basically, what that means is coursing it to the resolutions of the late 70s and coursing the modern data to match that, and then also do some recalibration processes with it, and then apply an objective or automated algorithm to use satellite data to estimate surface wind speeds. And this is based on seminal work by Vern Dvorak from the 70s and 80s. And it's used operationally globally and has been for many, many years. So if we apply that technique to the homogenized data, then we do in fact find significant and fairly large increases in global intensity. And so this is a relatively new result. In fact, it was just accepted just last week. The takeaway from this is that the probability of finding major hurricane intensity is increasing by about 8% per decade. And this is a statistically significant trend or increase. If we look at the same analysis using best track, it's about twice that. It's about 17% per decade. And so we can make the statement, with some caveats, that it seems like the best track data is, the trends in the best track data are about equally split between actual physical trends and the technological trends. So that's a interesting result to have, and it's somewhat similar to what we might have expected going in, knowing what we know about the best track data. The other important thing here, of course, is that this is consistent. What we are measuring now, these global changes in tropical cyclone intensity that we're measuring with homogenized data, is consistent with our theoretical expectations, and it's consistent with numerical modeling. So that starts to build our confidence that we are getting towards some kind of a detectable signal here. Another way to look at these changes in global intensity is to look at time series of the data. This is just a time series of the proportion of major hurricane fixes. On the left at the global signal, and there's a pretty clear trend. The proportion goes from about 0.32 to close to 0.4. And and it's highly significant statistically, and fairly robust to any outliers and things like that. It's always of interest to look at these signals regionally, although we start to get into reduced signal to noise ratios, and we also run into the problem of some of these strong decadal variabilities that operates regionally, and so it's difficult to disentangle what we're seeing. But here we're looking at the trends in the different ocean basins that support tropical cyclones. And you can see that all of the basins actually do contribute to the increase in trend and intensity, with the exception of the northern Indian Ocean. But the sample is extremely small there, and that trend is not at all significant. So it's not contributing a lot to the global signal. But the rest of the basins are consistently showing various degrees of intensification, and sort of arbitrarily put in the smooth indices for what we might say represents the multi-decadal variability in these various ocean basins. So you can see there's the Indian Ocean Dipole Index, there's what's called the Atlantic Multi-Decadal Oscillation Index, which is probably a misnomer since it probably is not an oscillation. And then there's the Inter-Pacific Oscillation. So you can see that clearly those particular indices have the potential to project a trend onto what we're measuring. And so when we measure these trends in the observations in the data, we have to always bear in mind that it's not clear what is forcing these trends and how much of it is being forced by natural variability and how much is potentially a human fingerprint. Okay, so there's other things that we can do. We try to be a little bit clever and think about, okay, what else is in the best track data that might be a little bit more reliable than those intensity measurements that have such problems. So we could introduce a metric and just say, let's ask the question, where are these storms when they're at their peak intensity? And the nice thing about that is that even though the word intensity is clearly in that statement I just made, the actual intensity is not that critical here. You just need to know that it's at its maximum. So the various biases that go into measuring intensity will tend to wash away in that case, right? You're just saying it's at its strongest point now. And another nice bonus to that is that these data, the best track data, are taken operationally. I should have mentioned that earlier, which is why they're so heterogeneous. They're taken in an operational setting using the best technology at that particular time, and this is done by forecasters in offices all around the world. And so they're going to be paying much better attention to these storms when they're at their peak intensity, compared to, say, Genesis, which they may be a little bit late to say, okay, I guess that's a tropical storm now, and it's a little bit harder to measure when they're that weak. Or Lysis, when they're dying, they might actually decide, well, let's stop tracking the storm because it's moving out over open water and it's not threatening land anymore. So there's a number of various problems that can creep into the data when you're looking at Genesis and Lysis points and things like track duration. But for lifetime maximum intensity, that should be pretty solid because people are paying attention at that time. So going into it, we would say this is probably a more robust metric for doing trend analyses. And when we look at trends in this metric, what we find is a very clear and significant poleward migration in both the northern and the southern hemispheres. This is a global signal, and this is not to say that no data issues can creep into this, but if we compare the best track trends to the trends found with the homogenized data, we actually find that they're roughly the same. So that gives us some confidence, whereas clearly they were very, very different when we looked at the intensity between the homogenized data and the best track. They weren't, the trends were twice the the best track data had trends that were twice magnitude of the homogenized data. Here, we're getting roughly the same. So we have a significant poleward migration. We just regressed ENSO out of this to get rid of the interannual variability. And so this is a residual time series, but you can see that the trends are very much the same and they're significant. And this is consistent with the expansion of the tropics, which is completely independently measured, right? In this case, the tropical cyclones can be used as little tools or bellwethers for measuring the expansion of the tropics. So that's kind of a neat sideline. It's an independent test. And again, we find that small changes in the mean can translate into large changes in the distribution. This poleward migration of tropical cyclones is particularly large in magnitude in the western North Pacific, and it also models tend to show the same behavior. But here, what we see is that you can get a reduction of tropical cyclone exposure at these lower latitudes, where you might have, say, the Philippines. And then a very small change in where the average latitude is, but then very, very large increases of tropical cyclone exposure as you get up towards the coast of eastern China and toward Japan. So this is a potentially very dangerous situation that we have here as these storms start to migrate into regions that don't necessarily experience so much as, say, the Philippines do. So it's good news for the Philippines and bad news for these other places. And it's not proportional, or it's not equal, because these places that are seeing more exposure, because they historically have less exposure, may not be quite as resilient to these threats. Finally, another metric that we might have a little bit more confidence in, because it's derived only from best track positions rather than intensity, is the translation speed. And as we mentioned earlier in the talk, there's perhaps an a priori expectation that these might be slowing down if the general circulation patterns are slowing down. And in fact, if we look at the translation speed globally and look at the comparison of early and late periods, we do in fact see a significant slowdown. There's been some work since this that has found, made some good arguments that some of this is probably related to some data issues, but there's still evidence that it's not completely explainable in terms of changes in the data. The model's agreement on this is mixed, although at the moment the evidence is building that slowdowns are being measured. Tropical cyclone translation speed slowdowns are being measured by models outside of the tropics. There was also some work that Tim Hall at NASA did showing that the frequency of hurricane stalling events along the east coast of the United States is increasing. And this, we saw with Harvey and Dorian and a number of other storms lately, Florence, that tended to stall out over or near land and create enormous problems because they were not moving. So this is a very, very dangerous situation to have storms slowing down. You want them to get out of your neighborhood as quickly as possible. So again, we said, well, what data do we have more faith in? If we feel like some of that global slowdown is caused by data issues, well, we have more confidence in the data all the way back to 1900 if we just look over the conterminous United States. And when we do that and we measure the translation speed of tropical cyclones over the US, we find a significant slowing, and it's 17%. It's quite large in the past 118 years. Now we can go ahead and regress out multi-decadal variability from this time series, and we're left with again a significant slowing trend. These are storms moving over land, so this is very, very dangerous. A slow-moving storm over the ocean, not so dangerous, right? Mostly what they're doing is churning up water and dropping lots of freshwater rain. but over land, this is a very, very dangerous situation. And if we think about the amount of rainfall that comes out of these storms is related to rain rate, and it's inversely proportional to the translation speed. So if we're saying that we're going to see a rain rate increase of, say, the Clausius-Clapeyron rate of about 7% per degree C of warming, and we have a 17% increase, decrease in the translation speed over that same time, then we get about a 29% increase in the amount of precipitation that is going to fall in any local region, right? This is more Eulerian than, or Lagrangian than Eulerian. We're saying that if you follow the storm around, that's your rain rate. But if you're measuring your rainfall, that's a location. So, and that's what matters, right? You can have a storm dumping lots of rain and moving quickly, and it doesn't really affect or flood places quite so much. This is a very dangerous signal that we're seeing here, and it's not clear how this is going to project into the future. So let's see, how am I doing on time here? Okay, I'm running out of time, but that's good timing on this. So to kind of summarize some of these results, and this is by no means complete. There's been an enormous amount of work that led to kind of where we are now in terms of where our confidences are. But where we are in terms of those confidences and the sort of things that will find their way into assessment reports is that in terms of the slowdown, the models are still inconsistent on that, but there's mounting evidence. More papers are coming out that are capturing a slowdown of translation speed at subtropical and higher latitudes. And that actually is consistent with the signal we're finding over the conterminous US, since the conterminous US is entirely either in the subtropics or the middle latitudes. The confidence is still presently low because this is all fairly new, but over the United States, the confidence is heading more toward the medium range, that there is a significant and potentially detectable slowdown over land there. We have much better consistency with the models at replicating poleward migration. It's medium that the signal is detectable in the Western North Pacific. The intensification of tropical cyclones, or the increasing intensity over time in warming scenarios, is pretty robust. We have a lot of consistency between physical understanding and models. The observed signal is significant. Attribution, of course, is still uncertain, but confidence is because of the combination and consistency that we're finding, we might go up to about medium, that we're seeing a detectable signal there. Ultimately, there's still plenty of uncertainty in the data, and this creates uncertainty in detection. But we are seeing evidence mounting, and the way that we're seeing these tropical cyclones change their behavior is almost always deleterious. It's very unusual to find cases where that's good news. And so it's clearly, given the impacts of tropical cyclones, and we all understand what those are, these changes have to be taken very seriously. And so I think the precautionary principle in this case is probably the way to look at what we're observing. And I'll stop there, and thank you for your attention.
Thank you so much, Jim. Appreciate the presentation. We've got a couple of questions that have come through here, so I'll go ahead and ask those for you. Any info on the expected occurrence of Southern Atlantic hurricanes following on Hurricane Katrina in 2004, the only recorded South Atlantic hurricane in history?
Yeah, if we look at how the environment is changing in that region, the sea surface temperatures are warming up, and that seems to be suggesting increasing likelihood of getting tropical cyclogenesis and intensification there. On the other hand, the vertical wind shear, which generally keeps a storm from developing, is also increasing in that region. So it's kind of a mixed bag in terms of what to expect. We do see model projections a lot of times start producing more of these storms in that area, but I think at this point it's a little bit unclear about how we should view the projections in the South Atlantic.
So we've got time for one more question here. What changes, if any, have occurred in the accuracy and precision of tropical cyclone intensity measurements have occurred over the past 40 years as technologies used in geostationary satellites have evolved?
Oh, well, yeah, I mean, absolutely. The satellite imagery has become increasingly better. It's spatially better, it's temporally better. We are able to measure intensities that we were not able to measure before. In addition to that, some of the procedures being used to exploit the satellite data to estimate intensity have improved over the years as well. So all of these things are significant factors in creating, like I said, at least half of that trend that we see in the instrumental data. To be clear, the homogenized data, all of those things are taken into account as best we can. And so the satellite data and all of the heterogeneity in those data are mitigated, maybe not removed completely, but certainly mitigated. So yes, absolutely, we have to be very careful of how to interpret changes in intensity given the changes in technology that we have.
All right. Jim, thank you so much. Very much appreciate the presentation.
Thanks, Rob.
We're going to go ahead and hand it over to Duane, who's going to present on a systems perspective on environmental prediction enterprise. Okay, Duane, you should have presenter capabilities. Thanks for joining us.
There we go. Can you hear me now?
Hear you great.
And the screen looks right?
Looks good.
All right. Thanks, everybody. And thanks for the organizers to have this sort of reprise and the opportunity to talk about this again. I'll say at the outset that this is not a science talk. It doesn't have science results in it or science conclusions in it. It's largely just a programmatic sort of set of observations and kind of suggestions and recommendations. And they've come about from 3 interactions that I've been involved with in the recent past. One of them is being part of what's referred to as the Earth Science and Applications from Space Decadal Survey. This is a survey, as indicated, that comes out every 10 years now. We've done the second one in 2018. And the important thing about this Academy report, and many of you out there have been on Academy studies and produced reports or read them, and they're useful and we can be very impactful at times. This study for Earth science, I think, stands apart in terms of its impact and driving capability for our community. It actually really almost verbatim guides at least $1 billion per year investments, I would say, because if you think NASA's Earth budget is about $2 billion per year, I mean, and the flight program side of it, the satellites, etc., probably at least half that. This is guiding that for the decade that follows, and it also has knock-on implications for NOAA and USGS. So this is a very big study, and it has a lot of impact, and it's a very complex study to carry out. It takes about 2 years, for example, and so it guides sort of the prioritization of Earth system or Earth science within NASA and beyond, and then it also helps prioritize the type of space-based and other remote sensing assets that are used for it. So that's one sort of pillar observation or interaction that this sort of talk is based on. The second one is that I'm also on the BASC, the Board on Atmospheric Science and Climate, and for the last couple of years, BASC has been considering a large-scale kind of analogous study on the weather enterprise. The weather enterprise is changing rapidly, both from a technology innovations, the complexity of all the different sectors that contribute to it and then benefit from it. And the scope of it is such that it just seems like it might be warranted to have a pretty overarching study on it, almost like a decadal survey. That's how it was proposed sort of initially in some of the initial discussions. And so as part of that, some of these observations you'll show have come about through the discussions with BASC and some other things in preparing for an earlier meeting to have that discussion. So this study is sort of still something that's being considered, and I make a suggestion or a consideration at the end of maybe how to consider this in the context of the other study I just mentioned. And now let's see. And a third pillar of this sort of interactions that flavor this talk are just the interactions I've had with system engineers at JPL. So I've been at JPL, so NASA, for about 15 years, and system engineering, for you not that close to it, it's a branch of engineering that's only been about 50, 60 years old, and it deals with requirements development, logistics, team coordination, testing and evaluation, costs, risks, optimization, and so forth, as much as you can imagine. And within the context of NASA, for example, building a space mission, you can imagine that a system engineer is fundamentally important. When I show a diagram like this, you can imagine they play a key role in helping develop the mission over its full life cycle and making sure everything works. And this is just a depiction on the left of kind of the life cycle kind of thing that's been going on at JPL for a few decades, and putting up the missions that you've heard about. And it starts in the upper left with sort of early formulation work, and then mission design, getting to a point design, then building the thing and integrating and testing it, and then launching it and implementing it and getting some element of science out of it. And you can imagine that the system engineers are part and parcel of this, almost a skeleton, a piece of the skeleton of something like this. And so I've been closer to this than I was before I went to JPL, and they play such an important role. And in earth science, we're finding that the utility and incorporation of systems thinking and system engineering principles and practices is getting to be more and more important because of the complexity of the Earth system, the science itself, and then even beyond that, what we're trying to do and all the tools that we need to utilize and so forth. And so in looking at this general life cycle that you can imagine applies to a space mission, in earth science, we've actually exercised this, not just JPL, but NASA and other countries, so many times that we have a lot of observations now, and we're trying to do a lot with those observations. And a lot of that comes from combining them with models to enhance their impacts and kind of interpolate and extrapolate to get other information. That's a complex process by itself, and deals with complex tools. And then once we do that, you end up needing information with uncertainties to either help you answer science questions or do applications where, it starts to get really important. What is the traceability to stakeholder and needs and so forth? Or you might just feed it back in and then look at the next round of observations you need. But this whole left and upper side of this diagram is something that we're starting to engage system engineers on in actually carrying out our science. So these three things, the decadal survey for NASA, it's a big survey. It means a lot. It has a lot of impact. It says a lot for our earth science community. The consideration to do something like that for the weather enterprise, given its complexity, and then this sort of more awareness of the methodologies and impact that system engineering can have. That's where these thoughts have arisen from, and sort of suggestions that you'll see at the end. So I want to try and make 3 points that suggest considering a systems perspective and adding that to our considerations of how to optimize and improve the weather enterprise, and you could even call it a systems of systems perspective. And one of those is just that the Earth system science that sort of sits at the background is fundamentally a system, and approaching it as such is something we do, but it can't be overemphasized. So I'm just going to point that out, that has an element that lends itself to systems consideration and systems engineering. The second one was when you actually kind of tear apart what the enterprise looks like, the weather enterprise, it's complicated. And other domains out there, whether it's communication, transportation, civil engineering, military, healthcare, they employ, bona fide real system engineers and approaches to deal with their systems of systems. And I don't see us as yet, maybe we could maybe do more to embrace that. The third one is, if you just look at the enterprise as kind of a data flow problem, it also highlights maybe some opportunities and focal points. And so it's just those three things to get at the point of trying to urge and nudge, maybe more embracing these types of methodologies more. And then at the end, or sort of the second half maybe, or last third, is add a couple other perspectives regarding our evolution of the weather enterprise that kind of stems from these systems perspective. In one case, and the latter is really more along the lines of how to think about a weather enterprise study and how it might dovetail with the decadal survey we have. So the first sort of tenet of just, why we might embrace a more systematic approach, and I think we already do this pretty effectively in this way, is just because the backdrop of weather models is really Earth system models, and they're growing in complexity to emphasize that element of the Earth system as a whole. And they sort of eventually will asymptote as we get more and more sophisticated with additional stakeholders driving needs and wanting to represent more processes, that our weather models will kind of asymptote to something that has a lot of Earth system components of it. And that's happening now, and there's recognition now that we don't really call ourselves weather centers so much as the National Centers for Environmental Prediction, or ECC, which is Environmental Canada, to recognize this sort of broader science underpinning what we might otherwise call a weather prediction model. And so just to emphasize that upper right is sort of the asymptote, or the driving aspirations for representing some of our Earth system components within weather prediction models, using that term loosely. And so this is just emblematic of a need to take a systems approach, break that system down, and sort of prioritize and look at it through that way. So I think we do that pretty good. That's one point that just emphasizes the element of a systems approach. The second one came about through, I mentioned that AMS summer meeting where we were talking about the weather enterprise study that BASC was considering, and I just sort of put this table together to initiate a discussion for a given session we had. And I just wanted to think about what the weather enterprise looks like as a matrix, where on one hand, along the top in columns, you have the tasks, all the tasks that go into the weather enterprise. And so they start with identifying and quantifying requirements in that first column, developing technology that could be space-based or in situ, and implementing it for observations. There's the data assimilation, development, and model improvement. Sort of model and data assimilation, development, improvement, a very hard task. Then there's the actual operational predictions. There's product development after the fact, and then there's reanalysis, development, and production, which does play into this a little bit. And then there's just basic research. And then along the vertical axis is all the people who play a role, people, institutes, and so forth. And if you this is just my stab at what this looks like if you were to fill it in. 3 X's means a bigger role than 1 X, and no X means not very much. You can see that there's a complexity, a significant sort of systems complexity to our weather enterprise. And it's not so obvious that we have an entity that can step back from that and look to optimize it. I wouldn't say any one entity on that sort of left side can easily step back from what they're doing and sort of look at this as a system and look at gaps and shortcomings and make sure it's optimized. The other thing it really highlights, which I'll point out in the next one, when you take this view of it, is how few X's are in the operational environmental prediction column. There's a lot of contributors to requirements definition and adding observations and so forth, and doing basic and applied research. But there's very few X's in that column, and that's really relevant for the next point. And just as I get to that next point, I want to point out what the entities are in that, and typically as viewed from the WMO, they'd be referred to as global producing centers, NCEP, ECC, ECMWF, UKMO, and so forth. And modern, the modern day versions of these, of which they often have environment in the name rather than just weather, there's a lot that comes out of them. It's not just 0 to 10-day predictions any longer. There's long lead predictions. Almost all of those have some form of a subseasonal prediction, whether it's experimental or operational. A lot of them also have seasonal forecasts with various parts of the Earth system represented, and a number of them are pursuing decadal forecasts. So these are very comprehensive systems that feed information for decision support. And so they'd say they're kind of seamless out to a year, maybe soon a decade. They're of course doing almost Earth system prediction or environmental prediction more than weather. And so there's a real consolidation of the guidance, the sort of environmental prediction guidance into these centers. And the core element of that, and you can almost call them implementing centers. I think I've pretty much covered that. So that's what these entities are. So they have a lot of outcome from these few 11 or 12 centers. So actually, that I forgot. I included a slide here that I also, just thinking about our weather enterprise, there's a report put out called the Federal Weather Enterprise by the Federal Coordination of Meteorology. And they this is just another indication that some systems perspective might be helpful. So what this shows is the amount of money spent by the different agencies on the weather enterprise. And the blue bars are all the US. And the ones on the left up until the big tall bar total are, you just rack and stack them and then you get the tall blue bar. And so this shows how much money, for example, we think we spend on the Federal Weather Enterprise and by who. And then the ones on the right are actually comparisons I found when I went out and looked and tried to find comparisons to that. And anyway, I mean, I think what our weather enterprise does in this country is great. And there's not the suggestion that we're spending too much, because look at JAXA only spends that much, or ECMWF only spends that much. And if you add those all together, it's not even as much as we do. And that's not the suggestion here. The suggestion is there's a lot of pieces to that puzzle that add up to that, and taking, again, more of a systems of systems approach might optimize those expenditures even more. So back to this, I just wanted to highlight this complexity, the fact that only a few players do this operational prediction despite the entirety of the enterprise, what those centers do. And now if we just sort of take another look, and this is a third part, that third perspective is, if you think about this from a data science and data flow perspective, there's something interesting, I think, here, is that when you think about all the observations as one element that play a key role in producing environmental prediction guidance, weather forecasts, you would measure that on the left. There's all sorts of observations that go into this. You would measure that in terms of billions. There's a lot of entities out there, a lot of radio sons, a lot of airplanes. That's a very complex landscape out there that you would, again, measure in terms of billions. On the right side, where you talk about impacts, almost however you cut it, you'd also could measure that in order of billions, whether it's mitigating losses, whether it's the amount of personal decisions made per day that are influenced by weather forecasting coming out of this system. So the impacts are ordered that way. What I find interesting is that because of this one column in that matrix, it says really only a dozen or so centers play a key role in providing guidance, keeping in mind that, yeah, these are the global centers. They might, take predictions out a long ways, but then there's a lot of things that hang off of that, like hydrology and chemistry models and all that. But these are the backbone. You measure that in order 10, and that take all the stuff on the left and turn it into all the stuff on the right. And to me, that really drives home the fact that more attention could be paid on just this sort of focal point to make sure we best serve the thing on the right. So that's the third thing. What are I doing on time? So So those are the three things that sort of in the weather enterprise, kind of suggest maybe a broader look from a systems perspective. I'm going to skip this part, but if anybody's interested, I tried to put some of this stuff in a sort of a semi-quantitative framework, and I won't have time to cover that. But if you're interested, let me know. And I want to just get to my last points, and which have a couple slides after this. So the three sort of observations I had were, applying more systematic, actual, the methods of this other field of system engineering to our enterprise might have value. It comes across because along the bottom, there's science complexity that suggests it's warranted. There's enterprise complexity that suggests it's warranted. And there's even data science considerations that suggest that it might be a good thing to look at. And there's massive societal benefits in the offing. And so doing the most we can would be useful. So that's that. And now another observation about the weather enterprise study and or the decadal survey and what this enterprise study might look like. This is just a quick, I don't expect you to read the words, but if you look at the evolution decades, the decadal trends of what are sort of observation systems, Earth science-based observation systems look like. They came from the EOS era description, the stuff that gave us the Aura, the Aqua, Terra satellites and so forth, that early 1997 period. Then there was a 2007 decadal survey. Then there was a 2017 decadal survey. And the upshot of that, if you start reading the language, the high-level description, you can see just a trend between, it's always the case that Earth system science has been the driver. But ever since 97 to 2007 to 2017, application societal benefits just keeps becoming more and more important. It hasn't become the driver in these surveys yet, but it's becoming more important to recognize to be an important outcome. And so we're going to have another one in 10 years. I'm just curious of where that's going to land. For this decadal survey, I told you it's very impactful. It drives a lot of investment in our community. Will science always be the driver? How deeply can a survey like that ever address applications? Meaning things like how do we translate more science into application benefits to society and all the complexities and interagency aspects? And then even if it started to want to do more, can one study adequately address both the science and the applications? And I mean, I was on the one in 2017. I think that would be hard to penetrate all the complexities of the application side, the decision support side, to the depth that's needed, and try and do both in one study. And so I already talked about the decadal survey. It's centered mostly on science, or Earth science and applications from space. It does a little technology and a little applications. But when and how will the applications and the decision support aspects really take a deep dive? And one might consider that the proposed weather enterprise study, and that weather enterprise and weather prediction is just, in the early offing of actual environmental prediction more broadly, that if such a study was posed, it could be the analogous arm for applications, an applications type deep dive, and go beyond even just a weather enterprise consideration. So that's my last slide. Thank you. I'll leave it here.
Thank you so much, Duane. Let me go ahead and pull up the questions here. Let's see. Okay, so we have a question. Is there any focus on the lack of diversity in the science, especially in tropical regions, in current surveys? If not, will this be addressed in future surveys?
Can you say the first part? I know I can't have a dialogue with the person, but can you say the first part again, the diversity element?
Sure. Is there any focus on the lack of diversity in the science, especially in tropical regions, in current surveys?
The science that's surveyed is pretty comprehensive. The construction of it was underneath the full panel. Underneath the steering committee were 5 panels. One weather and air quality, another one sort of ecosystems based, another one was climate, another one was hydrology, water cycle, and the other one was solid earth. And they're all quite comprehensive considerations of the state of the science and the gaps.
All right, thanks for the question, Marjan. Any other questions? We still have a few minutes to take questions. You can raise your hand using that functionality, or you can feel free to type your question in the questions pane. Right now, just some thank yous for the great presentations coming through.
Thanks again for hosting us.
Happy to, happy to. So we'll leave it open for one more minute. If you've got a question, feel free to send that through. In the meantime, I will go ahead and take back control, Duane.
Okay.
Do have another question here. Nope, no questions. All right, let's see. All right, so if there are no more questions, I want to go ahead and thank again Jim and Duane for their great presentations today, for taking the time to present to you all. I also want to thank Jim and Paul, their president and president-elect of the Atmospheric Sciences section, for helping to bring these talks to AGU and to you all and to our members. So the next webinar and the final webinar in the series will take place next Tuesday. You can register for it on the Atmospheric Sciences website. You can see that link right here. You can find the archive talks on the AGU YouTube channel as well. And this is some ways to stay connected with AGU, especially during COVID-19. We've got some resources up on our website to help all of our members. AGU staff is, as you can see, all working remotely during this time, so we are fully operational and able to assist you any way we can. The next webinar, again, is the final webinar in the series next Tuesday. It'll be Ben Santer and Brian Soden presenting with us. So that's it for today's webinar. Thanks to everyone for joining. Have a great rest of your Tuesday. Stay safe and be well.
Thank you.
Thank
Thanks
you, Duane.
again, Dave.
Thank you all.